Okay, we were looking at limits at infinity last time. So remember we talked about end behavior a little bit. We were talking about, I showed you that little demonstration of polynomial end behavior. And what we found is that as x approaches positive or negative infinity, it's only the leading term of a polynomial that really matters. All the other ones just get so small they're insignificant. So when we're trying to answer a question, this is where we left off last time, questions like this. We're trying to answer a question like, which power function models the end behavior of this function? We're ignoring what's going on locally, and we're just asking what's happening way out to the right or way out to the left, at the tails of the function, way the heck out there. And all we have to do is just consider the ratio of the leading terms, right? And so really this limit is replaced by, the limit of f of x is replaced by the limit of, and let me just change this slightly here. It's replaced by the limit of just the leading terms, which is 3x cubed over x, which just reduces to the limit of 3x squared, right? And so they would look, those two limits would be identical. If x approached infinity, the limit of f of x and the limit of the function 3x squared would look identical. Now they'd look very different in here, but way out at the edges they'd look the same, okay? Give me 1 to 5 on that. Okay, good. And then this is the last example we looked at. We didn't quite get time to finish this one. So this is a little different, right? Because this is not a rational function. All the previous examples we've looked at have been rational functions, polynomial divided by polynomial. Okay, but this is different. Now I've got a square root on the bottom. Okay, but the argument of the square root, meaning what's inside the square root, is a polynomial. And so if we take the limits as x approaches plus or minus infinity, inside that square root, the only term that's really going to matter, that's going to get really big, is going to be the x squared, right? Because we know that square roots, wouldn't you agree that if I just look at a square root function just by itself, if I just graph the square root of x, it just looks like that, right? So as I input bigger x values, the output y values also get bigger. Right? It's not a linear relationship, but does everybody agree that as x approaches infinity, y would also approach infinity there? The function would get infinitely high as we get infinitely far to the right. Okay, so given the fact that that's the behavior, then if this function inside the radical gets infinitely big, so is the radical, right? The radical is also going to explode. The only term that's really going to matter inside the radical is that leading term, that x squared term, right? So we could think about this then. In the limit that x approaches plus or minus infinity, the only term that's going to matter on top is going to be the 2x. On the bottom, the only part, it's not really saying the only term, but the only part that's really going to matter is the square root of x squared part. The rest of the x contributions, the rest of the contributions inside the square root are just going to be insignificant. The x squared is what's going to really matter as x approaches plus or minus infinity. Okay, and then we left off with the question, okay, well, what does that mean on the bottom? What is the square root of x squared equal to? And I think I got an answer of x, which is not correct. It's close. It's not even plus or minus. Okay, let's analyze this function a little bit. Let's just take this piece right here, and let's see if we can figure out from its behavior what that's equal to. Okay, let's just define some function. We'll just call it r of x. And it's equal to the square root of x squared. Well, let's just try a couple things. Let's try r of 4. R of 4 would be the square root of 4 squared. That's the square root of 16. That's 4. Well, it seems like x then, doesn't it? If r of x were equal to x, that would make sense. Okay, but let's try another one. What's r of negative 4? That's the square root of negative 4 squared. which is also 4, isn't it? Square root of 16. So what function do we know? If I input a 4, I output a 4. If I input a negative 4, I output a positive 4. Absolute value. Yeah, that's really the definition of absolute value, right? So what we end up getting here then is the limit of 2 times x divided by the absolute value of x as x approaches plus or minus infinity. Okay, what's that graph going to look like? Remember, we talked a little bit about this. It's been a while, maybe. The absolute value is a v. You're right. The absolute value by itself is a v, and then this would just be a line, right? Maybe that was with the other group. Maybe I was reviewing that with the other group. Okay, let's talk about this animal a little bit. This is a strange one. So I'm going to insert a little page here. We've got the function f of x equals absolute, no, it was 2x over absolute value of x, right? Wasn't that it? I'm pretty sure that was it. Okay, let's talk about the absolute value of x. The absolute value of x, how is that defined? It has 2 different types of behaviors, doesn't it? We get one behavior if x is positive and one behavior if x is negative. What kind of function do we know that describes that kind of a function where it's got 2 completely different kinds of behaviors? Can you think of a type of function that we used in the past? We haven't talked a lot about it this year, but we've done some. What kind of function could describe 2 different kinds of behaviors depending on the value of x, depending on the domain? A step function? Okay, step function is an example, yeah. Step function is an example of this kind of thing, a piecewise function, right? That's kind of what piecewise functions do. Piecewise functions allow us to describe different kinds of behaviors for different parts of the function. So the absolute value of x equals x when x is greater than 0, right? It equals 0 when x equals 0, and it equals negative x when x is negative, right? We have to multiply the x by -1 to make it positive if I input a negative. Everybody agree? Okay. So then, what's this going to do for me? If I'm choosing this f of x, I could also choose to write this as a piecewise function. It's equal to, if x is positive, what would that become? If x is positive, what would that absolute value function become? X, right? I just get 2x over x, which is 2. Okay. If x is negative, what would it be? The absolute value would be replaced by a negative x, right? And I'd get 2x over negative x, negative 2. Everybody see that? And then what about if x, can x be 0? In that function? What's the problem with having x equals 0? Can't divide by 0, right? Okay, so it can't be 0. So that's the entire domain of this thing right there. So we get this function that's it's kind of just a step function. It's this horizontal line. It's -2. It's equal to -2 if x is negative, and it equals +2 if x is positive. Okay, so let's go back here and take a look at this. So there's our function, right? There's the original function that we had. Here is a graph of what the limit looks like, right? We said that we could simplify the limit of this bizarre function up here, which might have all kinds of strange behavior. In the limit that x approaching plus or minus infinity, we just looked at the ratio of the leading terms, and we got 2x over the square root of x squared. Okay, well, what do you know? That's the same thing, by the way, as, we'll call it h of x equals 2x divided by, oops, absolute value of x. Notice that, I need a different color, don't I? Notice that the blue and the green are the same thing, aren't they? Right, just as we said. That's the definition of the square root of x squared is absolute value of x. So they look very different in this region, right? The blue function misses all this interesting behavior of our function around 0. But if I zoom out, doesn't matter. They look identical, right? They have the same asymptotic behavior. It's showing me the asymptotes, isn't it? Essentially what that's doing is it's showing me I've got these two asymptotes. I've got this asymptote y equals 2. The asymptote y equals 2, just that horizontal line, describes the right end behavior, and the asymptote y equals negative 2 describes the left end behavior. Okay, everybody see that? Give me 1 to 5 on that one. Okay, let's try another one of those. How about? Just gonna make one up. Okay, I want to find the horizontal asymptotes for that function. You guys walk me through the steps there. So what is that telling me to do? If I'm asking for horizontal asymptotes, how are we going to find those? Okay, good. Limits at infinity, right? So we're taking the limit of our function as x approaches plus or minus infinity, right? Okay, so let's do that. So the limit of this whole thing, I'll just call it f of x for a second here. Okay, what can I replace that with? My f of x. Okay, so that's going to become the limit of the leading term. So that's the square root of 7x squared divided by 3x as x approaches plus or minus infinity. Okay, and what's that become? Okay, so on the top, yeah, we got to use a little property of radicals here, don't we? The square root of 7x squared is the same thing as the square root of 7 times the square root of x squared, right? Something like that. And I don't really need to multiply them, but you get the idea? Okay. which is equal to the limit of the square root of 7/3 times absolute value of x over x, right? So this is a, like, if you understand how to think of this as a parent function, these kinds of problems get really easy to do. What the square root of x over x, let's go back to Desmos for a second. That's our parent function. Let's just turn all this other stuff off. And I'm going to define, I'm going to have to call it something. I'll call it p of x for parent. Right? That's all that is that parent function that's just a step function where I've got the positive step sits at y equals 1 and the negative step sits at y equals -1, right? That's it. So we're taking that parent function and we're just going to transform it. Well, if I multiply a parent function, if I multiply p of x, that whole thing, times 4, times 4, it just increases the amplitude by 4, right? If I multiply it by -4, it's just going to flip it over the x-axis and extend it by 4, right? So what am I multiplying it by this time? Well, I'm multiplying it by the square root of 7/3, right? So I'm just going to get vertical, I'm going to get asymptotes here. We'll do this as two separate limits. The limit of this function as x approaches positive infinity would just equal square root of 7/3. So that gives us the right horizontal asymptote is the line y equals square root of 7/3, right? As I approach negative infinity, what am I going to get? Well, that's just going to give me -1 out of this thing, right? So I'm going to end up with negative square root of 7/3, which tells me that the left horizontal asymptote is the line y equals negative square root of 7/3. Okay? And I see that right here just because I'm multiplying this step function by square root of 7/3. Okay? Good? All right. So real quick, which power function models the end behavior of that function? We'll call it p of x per, what's it going to be? 3x cubed? Look very carefully. Negative. Good. Don't forget that negative out front. So negative 3x cubed is what that thing, exactly what that's going to look like on the tails. Insides can be bizarre. Okay? Okay, what's the order of the polynomial that models the end behavior here? Or should say order is, we'll call it degree. I think we say degree. What's the degree of the first, wouldn't it, right? Yeah, 3x squared over x, so it's going to be linear. So we should expect linear end behavior. Okay, let's take a closer look. Same thing there, right? Okay. What if I wanted to find that end behavior? I know it's going to be linear, but what if I actually wanted to figure out what is, what's the exact line that's going to model that end behavior? Okay. We know, like if I look at this, go back to this example right here for just a second. So we know that the end behavior is going to be modeled by the ratio of the leading terms, which is just 3x, right? Okay. But what if I want to be more specific? If I actually divide this thing out, I've got a top and bottom polynomial that differ, where the top polynomial is 1 degree higher than the bottom polynomial. So we get this linear end behavior. If I divide this thing out, this is a good review for you, dividing polynomials. How would I go about dividing those polynomials? Raise your hand if you're a little rusty on dividing polynomials. Okay, all hands shoot up, right. Okay, so let's maybe take a little review of dividing polynomials. When we divide polynomials, there's 2 ways we can do this, right? We can use long division, or in certain cases we can use synthetic division. You guys learned synthetic division, right? Synthetic division is a real good shortcut when it's available. When can you use synthetic division? There's really only one limitation, only one time that you can use synthetic division, when the denominator is fill in the blank. I'll give you a hint. It would not work there. Why will it not work there, but it will work there? You want to take a guess? Say it again. Yeah, so synthetic division works here, but does not work there. Say it again. Oh, because this one has a coefficient? No, you actually, I'll show you guys that you even can. A lot of times people don't use synthetic division when the bottom has a coefficient, but I'll show you how you can. There's a trick for that's really not it. It's the fact that this is not linear, that it's got an x squared. You can only use synthetic division if the denominator is a linear factor, okay? So if it's a linear factor, let's review how we do synthetic division. Okay, so we make our, you guys, I assume you did it this way, where you just make a bracket for synthetic division. Is that how you did it? Okay. And then we're just going to put the coefficients of the top polynomial. We're going to write the coefficients on this top row. But we have to include all powers of x. So what would my coefficients be there? 3, 0, 0, right? That's the same thing as saying 3x squared plus 0x plus 0, right? And then out front, now here's another place where people sometimes get tripped up. The number that comes out front is the 0 of the denominator, right? We always have, you know, by our factor theorem in algebra, we always know that a factor always corresponds to a 0, right? So what is the 0 of the denominator there? If I set it equal to 0 and solve, what is it? Yeah, it's 2. Okay. So the number 2 goes out front. And now we start our synthetic process. Oh, and by the way, we always want to put our remainder box under the constant. Okay? So how did this work? What did we do for synthetic division? Remember? Okay, good. We seed the process by dropping the 3 down, and then we just start the synthetic process. So we get a 3 there. Anytime a number appears below the bracket, we always multiply by what's out front, right? So 2 times 3 is 6. And it's the opposite of long division. Instead of subtracting vertically, you always add vertically with synthetic. Okay? So 0 plus 6 is 6. 6 times 2 is 12. 0 plus 12 is 12. Okay? And what did that tell us then? What is this? We write this quotient. What's it going to be? What's the 3 and the 6 telling me? 3x plus 6, good. So this is telling me the remainder, this is telling me the constant, coefficient of x squared, coefficient of x cubed, and so on, if they were there, right? So the purple part is telling us 3x plus 6. The remainder part is telling us what remains over my denominator of x minus 2. Okay? Give me 1 to 5 on that. Is that all coming back? Okay. All right, so we could replace our function. We don't replace it, we're just rewriting it in this form, right? So now let's look at it that way. If we've got f of x equals 3x plus 6 plus 12 divided by x minus 2, or x minus 2, what if we're taking a limit of that? I guess I should have just done that all at once. What's the limit of this? 3x plus 6 plus 12 over x minus 2 as x approaches plus or minus infinity. Well, what happens to this term if x approaches plus or minus infinity? It goes to 0, yeah, right? And look what we get. We get the result. This is all that's left over. And I know what you're thinking. This one goes to infinity, so this one becomes insignificant. You're right. You're right. But this is what we call, if we keep the 6, this is what's called the slant asymptote. And if we keep the 6 there, if we just suppress that one term that's going to 0, then we get the exact equation of the horizontal line that this function is going to stick to. Okay? Now this isn't a horizontal asymptote, it's different. It's a slant asymptote or an oblique asymptote, sometimes it's called. Let's look at a graph of this function. You'll see what I mean. Let's graph this original function with its oblique asymptote or slant asymptote, and you'll see how useful it is. Okay, so we've got the function f of x equals 3x squared divided by x minus 2. Okay, so there's that function. Now let's graph our asymptote, 3x plus 6. Look what happens. You can see that thing start pretty quickly. That thing starts to stick to that slant asymptote. Everybody get that? Okay, that's pretty slick. That gives us a good skeleton for sketching that function. Okay, while we're at it, let's go back to this one. Are there any other asymptotes that would help me out here? Look at f of x. Okay, so what happens at 2? At 2, okay, so x equals 2 is a 0 of the denominator, but not the numerator. So what is that by definition then? Vertical asymptote. Yeah, there you go, right? So we know that we get a slant asymptote at y equals 3x plus 6 and a vertical asymptote at x equals 2. And again, if we go back to our graph, you can see right away how well that captures the behavior of the function. Isn't that cool? Look at that. Right? And just by seeing those asymptotes, there aren't very many things this function could potentially even do, right? What could it do? Either it's got to do what it actually does, or it could potentially have done something like that, right? Where it's just going to go like that and like that, but it doesn't leave you many choices, right? It makes it pretty easy to sketch. All right. Okay, so we could do the same thing with that, right? Could I use synthetic division there? I could, right? No problem. Could use synthetic division there to get the end behavior. And what's it going to be? It's going to be a line. It's going to be linear, right? I am going to get a slant asymptote here if I simplify that quotient. Everybody get that? That's all I'm getting at. How about that one? Am I going to get a slant asymptote there? I am. Sadly, though, can I use synthetic division here? No. So what do I have to go to instead? I got to go to long division. So we probably better review long division, right? Okay. Well, let's do that. So just before we do that, though, as a rule, for a rational function, if the degree of the polynomial in the numerator is exactly 1 greater than the degree of the that's supposed to say denominator, isn't it? Let me fix that. Then the quotient always simplifies to a linear polynomial. So we always are going to get a slant or oblique asymptote. All right, so let's try this one. Okay, so with long division, we set up our division template. What goes inside? Numerator, okay? Now, something you got to be really careful about here, you've got to make sure that when you're writing the numerator, which goes inside the division bracket, right? I think we call that the dividend. I can't remember which one it is. Dividend, I think, maybe. You have to include all the powers of x. You need to preserve a column for every power of x because you're going to be subtracting vertically, right? So you can kind of see, if you look into the future here, you can see you're going to need all those columns. So that's going to look like x to the 7th plus 2x to the 6th plus 0x to the 5th plus 0x to the 4th plus 0x cubed plus x squared. Whoops. Come on. Plus 0x plus 2. Okay, now what goes out front? Yeah, okay, good. Just the x to the 6th plus 1. I do not need to write all the columns out front. That's not important. I can just put the x to the 6th plus 1 out front. Okay, remember the process here is we're asking the question, how many times does the leading term outside divide into the leading term inside, right? So we're really asking for the quotient, what is x to the 7th divided by x to the 6th? Well, what is that? X. Okay, so that's telling me that the first term in my answer is x. Okay, anytime I get a new term on top, what do I do with that? Yeah, good, I'm going to distribute, right? I distribute that through the stuff out front. And that's going to give me, if I do that, I'm going to get x to the 7th plus x. Right? Now I'm going to subtract that whole thing, so I'm going to urge you to do this, because if you don't, you're going to make mistakes. Put the whole thing in parentheses and subtract it. And then we just subtract vertically. And of course, these have to cancel, right? We chose our leading term, so those would cancel. Then everything else is just going to subtract vertically. So I'm going to get 2x to the 6th minus 0. That just drops down. 2x to the 6th. All this stuff just stays the same. And then what's 0 minus x? negative x. Okay, and we do it again. So how many times does x to the 6th divide into 2x to the 6th? 2. Okay, so we get plus 2. We distribute the 2. I get 2x to the 6th plus 2. And I'm going to subtract that whole thing. So those guys cancel. I just get x squared minus x, and that's it, right? And now, does x to the 6th divide evenly into x squared? No, right? So what is that then? That's the remainder, isn't it? And we knew, if we look at the progression of the terms in our solution, we knew that the next step had to be the remainder because that's linear, right? We're going to go after a linear term. There's no place else to go, so you know it's going to be the remainder. And so we end up with this for our solution then. This whole thing is equal to the polynomial x plus 2 plus x squared minus x is what remains over my denominator, x to the 6th plus 1. Okay, make sense? So what's my slant asymptote for this function? X plus 2. There it is. Okay. Give me 1 to 5. How are we doing on that stuff? Okay. You got to practice it a little bit. I mean, you'll get a chance to do practice some division. Okay. When are we out of here? 25. Okay, that's a good place to end.